Welcome to Chapter 11, where we're going to have a brief introduction to computational chemistry. Now, this isn't my area of expertise, but I do want to at least give you a introduction and flavor of what we can do with computational chemistry and how it's done. And so computational chemistry is the idea that we can use computers to calculate properties of molecules. In particular, we're going to be looking at what's known as ab initio calculations. Ab initio stands for from first principles, it means that in Latin. And these are calculations that rely on the rules of quantum mechanics. And so essentially calculations here use the Schrödinger equation, H psi equals E psi, and we use the approximation methods that we've talked about. So this is all calculations that are done in computational chemistry roughly fall under the categories of variational theory, at least for ab initio calculations. So either they are variational theory calculations or perturbation theory. And so the ideas that we've talked about previously are what underlie these calculations that are done. And so the first thing that I'd like to talk about in this video is what's the purpose? Why do we need to do this? And computational chemistry can be quite expensive. It uses supercomputers sometimes, depending on the size of the molecules you're looking at or the level of approximation that you want to do. If you need something that's not super precise, you can do it on a personal computer. But if you want to get very accurate calculations of molecules, you often need a supercomputer and lots of time to be able to get the calculations. And so there are research groups all around the world that do computational chemistry, and that's all they do, and of all sorts of different types. So why? What's the purpose? So the sort of things that we can calculate based on computational chemistry, what can we calculate? So one of the main things that we can calculate about molecules are their geometries. So we can get a very detailed picture of the shape of a molecule, bond lengths, bond angles, right, that sort of thing, and know exactly what its shape is, provided we get the calculation correct. Another important thing, of course, are energies, right? Understanding the energies of the electrons in the, and the going with that, of course, since this is based on quantum mechanics, right, is that we get all the wave functions, or we could say the orbitals, right? We get a sense of where the electrons are in the molecule. And this can be very helpful if we're trying to find out things about its reactivity. Other things that we can calculate from computational chemistry are NMR spectra. We can predict what those will look like. Same with infrared spectra and UV vis spectra, right? Because we know the energies of the molecules. Those are things that we can predict what we would expect. And often this is a way to check whether these results are good and are correct, is do the predicted spectra from the computational chemistry model match what we actually observe? And one other thing that we can calculate are thermodynamic properties. And we do this using the theory of statistical mechanics, which lets us go from understanding what's happening with a single molecule and scale that up to a macroscopic behavior. So, that's a pretty big list of things that you'd like to know about molecules, and this shows the utility and why we do computational chemistry, why we build these supercomputers and use them for these purposes. And there are a lot more, more specialized and individualized applications of computational chemistry all throughout chemistry.